-50 degrees Celsius. Let that number sit for a second. That's not a weather warning. That's not an edge case in a laboratory simulation. That's the actual temperature at which Russia's newest helicopter, the Mi-171A3, was made to take off, fly, and land, repeatedly, in Yakutia, one of the coldest inhabited places on the surface of this planet. And here's what makes this genuinely remarkable. The helicopter didn't just survive those conditions, performed. But the cold temperature story is only the surface. Underneath it is something far more significant. A helicopter built entirely from domestic components, flying missions that foreign-equipped aircraft used to dominate, proving something that Russia's aviation industry desperately needed to prove, that it can do this on its own. If extreme aviation and deep technical breakdowns are what you're here for, subscribe right now and hit the bell. This one gets fascinating. Let's go. Before we talk about what the Mi-171A3 accomplished, let's establish something important. Why does testing in Yakutia matter so much? Why not a climate-controlled test facility? Why not a cold chamber that can simulate Arctic conditions in a controlled environment? Because controlled environments lie. Not deliberately, but they can't replicate the combination of factors that an aircraft encounters in the real world. The sustained cold that seeps into every material and every lubricant over hours of ground time. The strong, variable winds that change direction and intensity without warning. The poor visibility that reduces a pilot's reference points to almost nothing. The psychological pressure of knowing that the nearest maintenance facility is a very long way away. Yakutia provides all of this simultaneously, and it does it at scales that most of the world never experiences. Winter temperatures in Yakutia regularly fall below -40 degrees Celsius. During these trials, they dropped to nearly -50. To put that in perspective, that's colder than the surface of Mars on an average Martian day. At those temperatures, the engineering challenges facing any aircraft are genuinely severe. Metals, even those specifically chosen for cold weather applications, begin to behave differently. Their molecular structure changes. Ductility decreases. Brittleness increases. Components that flex safely at normal temperatures can crack under stress at extreme cold. Lubricants thicken. The oils and greases that allow moving parts to slide smoothly against each other at room temperature become viscous, resistant, sluggish at -50. Bearings that spin freely in a temperate hangar need significantly more energy to turn in Arctic cold. Transmission systems that operate silently in normal conditions can develop stresses and heating issues as they work against thickened lubricants. Batteries lose efficiency dramatically in cold. The electrochemical reactions that generate electrical current slow down at low temperatures, meaning batteries that provide full power at room temperature may deliver significantly less in extreme cold. For aircraft systems that depend on electrical power, avionics, communications, navigation, emergency systems, that degradation is a serious operational concern. And for helicopters specifically, there's an additional challenge that fixed-wing aircraft don't face. Rotor blades moving through cold, moisture-laden air accumulate ice. And ice on a rotor blade isn't just a weight problem, it's an aerodynamic catastrophe. The blade's carefully engineered cross-section, designed to generate lift efficiently, gets distorted by ice accumulation. Lift decreases. Vibration increases. And in extreme cases, ice can shed from one blade but not another, creating asymmetric loading that stresses the entire rotor system. This is the environment the Mi-171A3 was sent into, not to check a box, but to genuinely prove itself. The test program involved 66 flights and 22 ground runs. That's not a brief demonstration. That's an extensive, systematic evaluation designed to stress every system repeatedly under conditions that would expose any weakness in the design. And what did those 66 flights reveal? To understand what was being tested, you need to understand what the Mi-171A3 actually represents. It's a next-generation development of one of the most successful helicopter families in aviation history, the Mi-8 and Mi-17 series. If you've spent any time following global helicopter operations, you've encountered this family. They've been flying for over 60 years. They've operated on every continent. They've carried passengers, cargo, troops, medical teams, and rescue workers across some of the most challenging terrain on Earth. The Mi-171A3 inherits that DNA. But it's not just an upgraded Mi-17. It's a purpose-built platform for roles that the older designs were never specifically optimized for. Offshore operations, meaning the transport of personnel and equipment to oil and gas drilling platforms at sea. Search and rescue in remote, harsh environments. Combined cargo and passenger transport in conditions that would ground most rotorcraft. Each of these roles places specific, demanding requirements on the aircraft. And those requirements shaped every major design decision in the Mi-171A3. Take offshore operations first. Landing on an oil platform at sea is one of the most technically demanding helicopter operations that exists in regular commercial use. The landing platform is small, often less than 30 meters in diameter. It moves with the motion of the vessel or platform. It's surrounded by obstacles, cranes, superstructures, equipment. Wind conditions near offshore structures are turbulent and unpredictable as air flows around and between the platform elements. And if anything goes wrong, if an engine fails, if a hydraulic system malfunctions, if the pilot loses visual reference, the sea is right there. Performing this operation in normal conditions requires exceptional aircraft stability and precision navigation systems. Performing it in Arctic conditions, with reduced visibility, icing risk, and extreme cold affecting every system, multiplies the difficulty enormously. The Mi-171A3 was designed to handle all of it. But the design decisions that make offshore Arctic operations possible are worth examining in detail. Because they're not obvious. And they're not simple. Start with the airframe itself. The Mi-171A3 features a reinforced airframe, but reinforced in this context means something specific. It's not just thicker metal. It's a structural design philosophy that accounts for the kinds of stresses that emergency situations impose on a helicopter structure. What kinds of stresses? Hard landings. In offshore and Arctic operations, the scenario of an aircraft coming down faster than intended, due to power loss, control difficulty, or pilot spatial disorientation in poor visibility, is a real operational risk. A helicopter airframe that can absorb the energy of a hard landing without catastrophic structural failure can be the difference between a survivable incident and a fatal accident. The Mi-171A3's crash-resistant fuselage addresses this directly. The structure is engineered to deform in controlled ways under extreme impact loads, absorbing energy that would otherwise be transmitted directly to the occupants. The fuel system is equally critical. In a hard landing, fuel system integrity is one of the primary determinants of whether a survivable crash remains survivable. Ruptured fuel tanks feeding fire sources is how many helicopter accidents become fatal. The Mi-171A3's fuel system is specifically engineered to prevent leakage and eliminate ignition risk during hard landings. Then there's the flotation system. For a helicopter operating over water, which any offshore platform mission involves, the ability to float after an emergency water landing is the margin between rescue and tragedy. The Mi-171A3 includes an emergency flotation system that deploys automatically and keeps the aircraft afloat long enough for crew and passengers to evacuate and for rescue services to respond. In remote Arctic offshore operations, long enough for rescue services to respond might mean hours, not minutes. And finally, the seats. Energy-absorbing seats are a technology that's been developing in aviation for decades, driven by accident investigation data that showed how often occupant injuries in survivable crashes resulted not from the primary impact but from the deceleration forces transmitted through conventional seats. Energy-absorbing seats are engineered to stroke downward under impact loads, extending the time over which the deceleration force is applied to the occupant, and therefore reducing the peak force they experience. The physics are the same principle as a crumple zone in a car. The seat gives, so the person doesn't have to absorb the full impact instantaneously. In a helicopter that operates routinely over hostile terrain and open water, these aren't luxury features. They're what makes the risk of the mission acceptable for the crews who fly it. Modern helicopters are, in important ways, flying computers. The mechanical sophistication of the rotor system, The engines, the transmission, these are the foundation. But what makes the difference between a helicopter that can safely fly challenging missions and one that can't is increasingly the avionics and sensors that support the pilot's decision-making. The Mi-171A3 is equipped with a comprehensive suite of domestic avionics, a significant point that we'll return to. For now, let's focus on what these systems actually do. Navigation accuracy is the starting point. In Arctic and offshore environments, GPS reliability can be affected by atmospheric conditions, and conventional visual navigation is often impossible due to poor visibility, featureless terrain, or total darkness during polar winter. The navigation systems in the Mi-171A3 maintain accurate position awareness in these conditions, ensuring that crews know exactly where they are even when they can't see where they're going. Situational awareness systems go further. They integrate navigation data with terrain information, obstacle databases, and sensor inputs to give pilots a comprehensive picture of their environment, including elements they can't directly see. The ground proximity warning system is particularly critical here. In conditions of poor visibility, whether from fog, blowing snow, or low cloud, controlled flight into terrain is one of the most persistent dangers in helicopter operations. A pilot who loses visual reference can inadvertently descend toward the ground without realizing it until it's too late. The ground proximity warning system monitors the helicopter's altitude and rate of descent continuously and provides immediate alert when the terrain clearance becomes dangerously small. In Arctic operations, where a whiteout can reduce visibility to near zero in seconds, this system isn't a backup. It's a primary survival tool. Communication systems, reliable connectivity in remote regions, complete the picture. In areas with no cellular coverage, no VHF repeaters, and potentially degraded satellite communication due to atmospheric conditions, an aircraft that loses communication contact is essentially invisible to the outside world. The Mi-171A3's communication systems are designed for reliability in exactly these conditions. Here's the detail that makes all of this especially significant in 2026. Every single one of these systems is domestically produced. Let's talk about what fully domestic configuration actually means, and why it's harder to achieve than the phrase suggests. Earlier versions of the Mi-171 family, like many Russian aircraft programs, relied on foreign avionics and systems for some of their most sophisticated capabilities. Western avionics in particular offered capabilities that domestic equivalents hadn't yet matched. Advanced navigation systems, sophisticated autopilot functions, modern display technology. When sanctions eliminated access to those foreign systems, the choice was stark. Accept a capability downgrade and build aircraft with inferior systems. Or invest in developing domestic alternatives that could match the performance of what they replaced. Russia chose the harder path. And the Yakutia trials are, in part, a demonstration that the harder path was worth taking. The onboard electronics, hydraulic systems, communication modules, navigation systems, and terrain awareness technology on the Mi-171A3 are all domestically developed. But, and this is the part that often gets glossed over, developing domestic alternatives isn't just an engineering task. It's a systems integration challenge of enormous complexity. Think about it this way. When you replace one component in a complex system with a different component, you don't just need the new component to work in isolation. You need it to work with every other component it interfaces with. Different signal protocols, different data formats, different power requirements, different physical dimensions, different certification histories. Each domestic replacement creates a cascade of integration requirements that extend through the entire system architecture. And each integration point is a potential failure mode that has to be tested, validated, and certified before the aircraft can carry passengers. The fact that the Mi-171A3 completed 66 flights and 22 ground runs in -50-degree conditions without the domestic systems causing problems is the real proof of concept. Not the design specifications, not the laboratory test results. The actual performance in conditions that replicate, and in some respects exceed, the most demanding scenarios the aircraft will face in real operational service. But import substitution isn't a finished story. It's an ongoing challenge with dimensions that go beyond engineering. Step away from the engineering for a moment. Who actually needs a helicopter that can operate at -50 degrees? And why does it matter to them? The answer starts with oil and gas. Russia's hydrocarbon resources are, to an extraordinary degree, located in places that are extremely difficult to reach. Siberia, the Arctic shelf, the far north and far east. These are not regions with road networks, port infrastructure, or convenient logistics chains. They're regions where the primary means of accessing offshore platforms and remote facilities, year-round, in all weather reliably, is aviation. For the companies operating these facilities, helicopter reliability isn't a performance metric. It's a production metric. A helicopter that can't fly in Arctic winter conditions doesn't just inconvenience workers. It potentially halts operations entirely, delays crew rotations, and in emergency situations, eliminates the primary means of rapid response. The Mi-171A3's ability to land on offshore drilling platforms is, therefore, not an optional capability. It's the core operational requirement that justifies the aircraft's existence. And the economics of getting this wrong are severe. An oil platform with hundreds of workers, operating production equipment worth billions of dollars, in weather conditions that can become dangerous without warning. If the helicopter that connects them to the mainland can't fly, the entire operation becomes more vulnerable. Beyond oil and gas, search and rescue in Russia's remote northern regions is a mission profile where the stakes are even more direct. In many areas of the Russian far north, aerial rescue is simply the only option. There are no roads. Rivers may be frozen or in flood. Ground-based emergency response can be days away. When someone is in distress, a worker injured at a remote site, a vessel in difficulty on an Arctic waterway, a community cut off by weather, the helicopter that responds is often the only thing standing between that person and a very bad outcome. For search and rescue, every performance specification translates directly into lives. Endurance, how long the helicopter can stay airborne, determines the search radius. Payload capacity, how much it can carry, determines whether it can bring back multiple casualties or only one. Navigation capability, how accurately it can find a specific location, determines whether it reaches the right place before fuel becomes a constraint. And all of these capabilities have to work at -50 degrees in strong winds in poor visibility. The Yakutia trials were, in this sense, not just a technical validation program. They were a demonstration of operational readiness for missions where failure isn't just a program setback. It's a human tragedy. So after 66 flights and 22 ground runs in conditions that pushed every system to its limits, what did the evaluation actually show? The headline result is consistent stability throughout the test program. But what does that mean in engineering terms? Stability for a helicopter encompasses a wide range of behaviors. It means the rotor system maintained controlled, predictable behavior throughout the flight envelope, no unexpected vibrations, no resonance issues, no control anomalies. It means the engines maintained reliable power output despite the cold-induced challenges to combustion efficiency and turbine behavior. It means the transmission systems, fighting against thickened lubricants in extreme cold, maintained the power delivery that flight operations required. It means the avionics stayed functional. Signal processing worked correctly despite the effect of extreme cold on electronic components. Display systems remained readable. Navigation maintained accuracy. The ground proximity warning system responded as designed. It means the anti-icing systems, protecting the rotor blades from the ice accumulation that can degrade aerodynamic performance, worked effectively throughout operations in the cold, moist air conditions of Yakutian winter. And it means the crews, flying from Yakutsk airport and a remote test site exposed to strong winds and severe conditions, were able to operate the aircraft consistently and safely throughout the evaluation. 66 flights, 22 ground runs, temperatures to -50, no critical failures, consistent performance. That's a result that matters. Not because it proves the helicopter is perfect, no aircraft is, but because it demonstrates that the combination of domestic systems integration, cold weather engineering design, and operational capability works in the conditions the aircraft will actually encounter in service. This is the point where the honest analysis has to acknowledge what the Yakutia trials don't resolve. Because the cold weather testing, impressive as it is, represents one phase of a much longer validation process, and some of the hardest challenges lie ahead. Building and maintaining a fully domestic supply chain for an aircraft like the Mi-171A3 is genuinely complex. The avionics, the hydraulics, the communication systems, the navigation technology, each of these comes from domestic suppliers who need to maintain consistent quality, consistent delivery, and consistent capability development over years and decades of production. A supply chain is only as strong as its weakest link. And in a domestic ecosystem that's been built rapidly under pressure, identifying and strengthening those weak links is an ongoing process. Then there's the question of global competitiveness. The Mi-171A3 has demonstrated domestic certification track performance in extreme cold conditions. But international acceptance, sales to operators outside Russia, operations under international regulatory frameworks, requires a different kind of validation. International certification processes, particularly those aligned with EASA or FAA standards, have their own requirements, their own timelines, and their own expectations of documentation and transparency. Whether the Mi-171A3 pursues international certification, and whether it can meet those standards with its domestic system configuration, remains an open question. And there's cost. Domestic supply chains that are still scaling up production may not yet achieve the cost efficiency of established foreign suppliers who've been optimizing their manufacturing processes for decades. Higher unit costs affect the economics of the program, the prices operators pay, the competitiveness against alternatives in markets where alternatives exist. None of these challenges are fatal, but they're real. And the Yakutia success, as significant as it is, doesn't make them disappear. What it does is establish a foundation of demonstrated performance that makes everything else worth working on. There's a particular kind of proof that only extreme conditions can provide. Laboratory tests tell you what a system can do under controlled, optimized circumstances. Simulation tells you what models predict. Documentation tells you what engineers intended. But -50 degrees in Yakutia, with real wind, real ice, real cold penetrating every component and every joint and every lubricant, that tells you what the aircraft actually is. And what the Mi-171A3 actually is, after 66 flights and 22 ground runs in some of the harshest conditions on Earth, is this: a domestically configured helicopter that works. Not perfectly, not without challenges ahead, but genuinely, demonstrably works in the exact conditions its operators will face in real service. For Russia's aviation industry, that matters enormously, not just as a technical achievement, but as a statement about industrial capability. The Mi-171A3 shows that domestic avionics, domestic navigation systems, domestic hydraulics, all integrated into a coherent, functional aircraft, can perform to the standards that demanding operational roles require. For the workers who will fly on this helicopter to Arctic platforms. For the crews who will fly search and rescue missions in polar winter. For the communities in Russia's remote north who depend on aviation as their lifeline to the rest of the country. The Yakutia trials represent something very specific and very important. The helicopter coming to serve them can handle what they live with every day. As Arctic operations continue to expand, as climate change opens new maritime routes, as resource extraction pushes further into polar regions, as remote communities need more connectivity, not less, the demand for aircraft that can genuinely operate in extreme cold will only grow. The Mi-171A3 has just proven it belongs in that conversation. But here's the question I want you to sit with. In a world where Arctic aviation is becoming more strategically important, where multiple countries are developing capabilities for polar operations, does domestic certification of performance like this eventually translate into global relevance? Or does the Mi-171A3 remain a powerful tool for Russian operators that the international market never fully engages with? That's the question the next chapter of this story will answer. Drop your thoughts in the comments. Genuinely want to know what you think. And if this kind of honest, in-depth aviation analysis is what you're here for, subscribe, share this with someone who cares about aviation, and hit the like button. Takes 2 seconds and it genuinely matters. See you in the next one.